Thanks for introducing. Hope you guys had a great lunch, and I know session after lunch is probably one of the most difficult one to attend. So let me try my best to keep you guys awake. So let's get started. So today I'm going to talk about reliable data ingestion in Datalake. So before I start, let me give a brief overview on who we are. So Paytm is India's one of the largest, you can say, digital payment platform, wherein we provide digital wallet service, which you can actually pay to merchants directly from your wallet, so no need to carry your actual physical wallet. You can just directly pay via mobile. We provide payment bank services, payment gateway, Paytm Money, which is more like mutual funds buying via app, then e-commerce, recharges, travel, hotel, etc. And you can expect new verticals getting added frequently in different line of businesses, because it's a fast-growing company, and there's a lot of you can say happening across the company level. We have almost 330 million plus registered users, and together across these services, they generate a lot of almost multi-terabyte data on a daily basis. So today's agenda would be to start with typical ingestion requirements. How do you bring data from different sources to data lake? And I'll start with talking about traditional mechanism of how we have been doing these ingestions from different sources and what were the challenges associated with them. And then finally, I'll talk about the Spark-based ingestion platform that we built at Paytm to kind of solve some of those challenges that were there with traditional mechanism. So let's start first with the ingestion requirements. So what you see on left side are different types of data sources. You can have data sources like MySQL, Oracle, Salesforce, Google Analytics, Kafka, Amazon S3. Also, you can have some third-party source like Branch.io, OneDirect. You can also have Alibaba's cloud like OSS, which is similar to S3, SFTP, Zendesk, etc. There can be many more sources. I've just listed few of them that we ingest, but yeah, there are more sources that we ingest as well. And these sources will have their own, you can say, protocol to connect to talk to, and they'll have their own format of data that they keep data within their storage system. And what we have to do as an ingestion system is kind of bring all those data to central data lake. Typically, data lake could be Hadoop-based data lake, but not mandatory. In our case, yeah, it's a Hadoop-based data lake, and we have Hive tables which we expose to end users, and the data is kind of stored in Parquet format. So there are different consumers. Once you have kind of brought this data into data lake, you'll have facts and OLAP jobs, which would typically kind of try to join this data and flatten this data, and then you may have some hourly or you can say daily reports getting generated out of it. You may have some recommendation jobs, predictive modeling, fraud, ad hoc analytics, etc. So these are different use cases that kind of read data that have been ingested from the ingestion system. Typically, we have seen two types of ingestion mechanisms. One is like full ingestion, wherein you just dump entire data from source to destination, and these are typically small tables which have just metadata tables or configuration or high level, you can say they do not have transactional level details, but just rather kind of static tables. So you periodically dump entire table as a whole, and they do not require any kind of checkpointing because you are dumping the entire table in every run. But then there are incremental ingestion as well, which requires checkpointing. It needs to remember what was my last state so that I can do an ingestion incrementally in next run. And it may be with or without compaction. I'll talk about more on that in later slides. When you're also ingesting from these sources, there will be kind of set of configuration each source will have. For example, MySQL Oracle will have host, port, username, password. Kafka will have broker, host, and topic. S3 bucket key, access key, and SFTP will again have its own set of properties. And they will also have checkpointing mechanism of their own. So for MySQL, if you are, let's say, ingesting based on a timestamp column for incremental ingestion, then you'll probably need to remember what was my last timestamp till which I have kind of ingested, so that in next run I can take data greater than that timestamp. And for Kafka, it would be offsets. For S3, it could be directory structure, wherein if a directory is lexicographically sorted, then you'll probably keep the last directory name, and then in next run you'll find out the new directories that have been added in the bucket. So these are kind of requirements of an ingestion system. Now let's see how we traditionally have been doing ingestion. So in most cases, what you do is you start off with specific tools that have been designed for to connect to those source and fetch data. So for MySQL Oracle, Scoop is probably one of the most popular tool to ingest. And then for Salesforce, you might use some kind of Python scripting to connect to Salesforce API and get data and then dump it to Hadoop Data Lake. For Kafka Connect is one of the option to dump data from Kafka to, you can say, Hadoop Data Lake, and S3 may have its S3 client API. So these are different mechanisms from some of the source. Similarly, other sources will have their own mechanisms. And then you may schedule them, these sources, using some cron-based scheduling, or you may even use some open source scheduler to kind of schedule it. So what are the challenges? What's wrong doing this way? What we have seen is when you do actually in that way, there's kind of separate source code that you have to maintain to kind of do ingestion, and especially when you are doing it at a scale. Let's say you have 5K tables or 10K tables. You can just imagine the kind of variety of sources and volume of sources that it can create a mess with. So what are the problems? So first of all, when you have more code, it results into higher chances of bug. You have custom configuration. I'll talk about different configurations like host, port, broker, and all those things. So when you do that in a custom way for every source, you need to figure out how to store those configurations and how to store that securely, so that if you're using credentials, you do not end up kind of keeping them in a plain text file, but probably you would want to do them in a secure way. Again, checkpointing I talked about. Each source will then have its own way of doing checkpointing. One of the important thing is transformation. How do you apply transformation? Let's say you are doing a scoop job on MySQL, and you want to mask certain fields before they get ingested. You probably would be doing that in the SQL layer of the scoop job configuration. And for Kafka, you may be kind of using, let's say you're using Kafka Connect, you might be doing SMT, single message transformation, but it will have its own way of defining the transformation. So when you're doing with so many sources, it adds a lot of complexity on remembering on how to do that with specific to that source. Not to mention about failure handling, scheduling, retry, backoffs. All of this probably would be handled separately because you don't have any common code base. And lastly comes sanity checks. How do you make sure that your data is correct in Data Lake? Again, if you do not have a common framework, then probably you will be doing that separately for each source as well. There are a few more challenges, especially around schema management. We have seen in our case that schema may get modified very frequently at source. There may be new columns getting added. There may be, at sometimes even there may be modification in an existing column. Let's say somebody changed from int to big int because they now realize that the range of the records that they're supporting is going to go beyond integer range. So they just change their data type. But that creates problem at Hadoop Data Lake, because if you have data in, let's say, Parquet file, you cannot have within same table int and big int both. You probably would need to transform existing data as well in the new format and then kind of rewrite it. Then if you're doing ingestion very frequently, let's say every hour or 2 hours, there can be a possibility of inconsistent read as well when you're doing a write if you do not take locks. But if you take locks, then it adds another issue on the performance side. So we'll talk about how we try to fix that. And one of the common things we have also seen is around backfilling or re-ingestion. That means specific time frame you want to go back and do a re-ingestion. Then again, for these sources, since there's no common thing, you may end up doing it in a different way. So that's where we try to solve these challenges with Spark-based ingestion platform. So let me first talk about why Spark. So Spark provides you a data source API to connect to various sources. So what we have seen is in 80% cases, we already have some mechanism of connecting to those sources and reading data. So we don't really have to write a lot of new code. But yeah, in some third-party SaaS application where it may not be there, we might have to do some custom development. Biggest benefit of Spark is a unified way of adding transformation. So once you have created a data frame, you can now add transformation in a unified way. You do not need to really worry about whether it's coming from MySQL or Kafka, as you had to worry for Scoop and Kafka Connect. But in Spark, you can just do it in a unified way. How? We'll talk about that. Spark also, Dataframe also has like schema. So you can do schema management, schema evolution as well. And one of the things that we also use is max record time or processing time, which we use to do dependency resolution in the downstream jobs. What I mean by that, I'll just come in coming slides. So this is a high-level architecture of our system, how it looks like. So I'll just quickly go through it and then zoom in each of some of these components which are critical. So on left, we have dataset service, which is a kind of metadata or catalog service. You can also call it a meta store. And on top of it, we have a UI for easy onboarding to Datalake. So it just provides all the tools that you can go and from the UI, you can just select a source, a database, table, so you don't have to do any configuration manually. And on top of it, we have custom scheduler, which gets this newly onboarded dataset from dataset service and then schedules via Livy REST API to Yarn cluster. And these are like actual Spark jobs, Spark-based ingestion jobs, which does the actual ingestion. And then they write data in Hive Parquet format. And along with that, we also have Spark-based Sanity jobs, which periodically does the Sanity along from the source and publish those results again in dataset service. And then finally, on the or you can say the lowermost layer, are the consumers who consume this data from Data Lake and also fetch metadata from these meta store, which is dataset service. So let me zoom into some of these components so you have better idea of what I really mean by this architecture. So dataset service is basically the main, you can say, central data management service, dataset management service, not data. It just manages metadata about a dataset. It provides an API to connect to source and fetch the metadata for easy onboarding so that you do not have to supply all these configurations manually. Manages metadata like state checkpointing. I talked about checkpointing for different sources. So it does that in a unified way. You can define a template for each source, and then you do not need to worry how do I save those checkpoints or how do I manage those configurations. They are managed by a central API. It also keeps a track of max record or processing time at a dataset level, which can be used for dependency management. So what I really mean by dependency management, let's have a brief discussion on that. So let's say you want to generate a marketplace fact OLAP, which is more like, you can say, of fact or OLAP, which is more like joining different raw tables and kind of creating a flat view, and maybe also adding some aggregations on top of it, which would be used by, let's say, different consumers. And what we want to ascertain is that if this job is going to get triggered at 9 a.m., then it should have dependent tables. Let's say it depends on sale order payment, refund, merchant, et cetera. It expects data up till at least 8 a.m. for each of these tables to be available in Data Lake. Now it needs that guarantee that yes, it is available, then only I'll get triggered. Otherwise, I'll wait for another 15 minutes or half an hour, whatever the configured, you can say, delay time. So in order to get that surety that data for dependent tables is available, it needs to fetch this data from some metadata service. And that's what this dataset service provides. It captures those metadata for these tables, and then you can add dependency and query whether my dependencies are met or not. It can just return you in true and false way. And in that way, it also captures kind of lineage that this dataset is derived from these different type of datasets, and it also captures like what frequency they are kind of getting scheduled. You can also activate, deactivate a dataset, so you can manage everything from a service. Then it also tracks history for changes, schema changes, config changes, anything, so that you can do debugging if required. And even you can register transformations. What kind of transformations? I'll talk about that in coming slides. So it's kind of central metastore service which provides all kind of dataset management operations. On top of it, we have custom scheduler. This scheduler actually talks to dataset service periodically and fetches the dataset that needs to be scheduled. Now these are mostly, let's say, it provides different scheduling mechanism. One of them is SLO-based scheduling. What is SLO-based scheduling? Let's say you define that dataset SLO is 4 hours, then in no condition you would want my dataset in Data Lake to be having a data older than 4 hours at source. There may be some business critical reports dependent on it. So you would want to make sure that no scheduler should schedule this to make sure that whatever is the runtime, let's say for ingesting this data set, it may be having a 20 minute of runtime, then it should cater to that, it should actually use that historical run time frames and make sure that it schedules in a way that it doesn't breach its SLO. In some cases, we also have high priority scheduling, wherein some business critical reports we cannot afford to delay our scheduling or ingestion, whereas there may be some other data sets which we are fine, they're not that critical. So in case you have very high cluster resource usage, your scheduler will still go and schedule the high priority ones first. There is also another thing we have seen is with respect to max connections. So in database, we have seen that when we pull data from slave databases, they provide us some limited connections, let's say 25 connections or 30 connections. And there may be maybe 15, 20 ingestion jobs that you want to run from that database. So scheduler takes that also into consideration that my particular job is going to consume so many connections, so I should ingest tables from the same database in a probably sequential way until the upstream already running jobs are kind of finished. So all those kind of custom scheduling mechanism is built into this scheduler. Then finally, once it had identified set of data sets which needs to be scheduled, it would kind of schedule these Spark jobs using Livy REST API. So we leverage Livy because that gives us a kind of modularity in the entire design. We can just write our scheduler independently on how do we kind of actually schedule these jobs. So Spark jobs can run on Yarn, but scheduler can be maybe an AWS Lambda based. It could be some other technology, whatever. So yeah, so that gives kind of modularity. And then it also adds retries, backoffs, all these is implemented. So now when we are doing this, we are actually, all we are bothered for is one Spark code that we need to schedule. It doesn't really matter whether it's going to kind of ingest data from MySQL, Kafka, S3, or whatever. So we can leverage just one common scheduler. Now comes the core part of this ingestion system, which is Spark-based ingester. So let's talk a little bit in detail about this. What is it? So this Spark-based connector or Spark-based, you can say, ingestion architecture has 3 layers. First one is the source layer, which is supposed to read data from source. Another is a processing layer, which we do some level of processing. I'll talk about that. And finally is a sync layer. So let's start with the source layer. Source layers is built on the concept of connector architecture, wherein we have a connector interface, and that interface is supposed to be implemented by the respective source connector. Let's say you have MySQL, then there will be MySQL connector, Oracle connector, Kafka connector. Similarly, for all sources, there will be connector. And what these connectors are supposed to do is kind of create a data frame based on last checkpoint from the source. So let me briefly talk about some of the responsibilities of these connectors. So first of all, they are supposed to fetch these connection properties from Dataset service. So you can see at bottom we have a Dataset service. It's again a central meta store, so all kind of configurations are stored there. And for credentials, we kind of encrypt credentials using KMS. So that they are kind of not exposed in plain text. But connector can be rest assured that when it is handed over these credentials by framework, they are kind of already decrypted. So they can just keep those credentials in memory and connect to source. Once they have connected to source, and let's say they have read some metadata about the source, maybe in case of MySQL, it could be finding the max timestamp and comparing it what was the last checkpoint, so that they know, yes, there is some new data arrived at source, so that they can ingest from it. So using that, then they can create a data frame. For that, they can leverage existing Spark, you can say, data source APIs. For example, in case of MySQL, you can use Spark JDBC source. For S3, let's say you're reading some JSON files or CSV files, Spark already has no respective data source APIs for them. But in case there is not something not available, then we can always write our own. Connectors are also supposed to throttle based on a batch size. So let's say you want to do a historical ingestion for a table. You cannot just go and say, okay, give me entire 1 billion records from MySQL and dump it to Datalake. But you rather will have to do it in a batch way. You probably would go in 1 million by 1 million, and once you're done, then you can continue with the new records that are coming in. So those kind of throttling mechanism is also that the connector is supposed to provide. The same goes with Kafka also. You may not be wanting to ingest everything in one go, but rather in batches. So that is again connector specific stuff, which goes in connector layer. It also captures new checkpoint, so that next run, you can start from the same checkpoint. And optionally, it may also capture max record time to use it in the downstream layer that we talked about, like dependency management. So once connector has created this data frame, it hands over this data frame to processing layer. What does processing layer do is basically there are primarily three steps. One is transformation. Now again, to do these transformations, we provide a UI where people can register. You can say Spark code as a transformation. We hand over the data frame object to the respective transformation layer, and they can simply write what kind of transformation they want. For example, here you see now we are converting to a timestamp column. Let's say what we are getting from source is some kind of string column as an updated at, but we want to kind of typecast or convert it into timestamp. Again, we want to typecast some other columns to long type. We may want to even mask some of the columns, like phone number is a sensitive number, it's a sensitive column, so let's mask it using MD5. So these kind of code snippets you can provide. So this gives you liberty that you can do any kind of transformation. Now you do not need to do any source-specific transformation that you had to do in a traditional mechanism. We think with Spark, once a data frame has been created, any transformation you do, it's kind of get auto-applied for all different sources. So to do this, we leverage Scala's Toolbox API, which provides you a mechanism where you can read this string of code and convert it into AST, and then finally compile and run this AST at runtime. Post-transformation comes schema evolution. Schema evolution basically, again, is simple with Spark because what you get is a data frame with schema object. So we compare two schemas, one that we get the data frame from source, and another data frame which is already existing in the Hadoop data layer in the form of Parquet files. We read data frame from there as well and just compare two data frames and figure out what has happened, whether a new column has been added or whether a data type of an existing column has changed. So if a new column is added, it's not that big a problem. But if, existing column has changed, that's a problem. So for that, we kind of rewrite the existing layer, you can say Parquet files with the new type by casting existing type with the new type. For example, you can cast int into big int. So that has already been applied. So just a kind of auto schema evolution that framework already takes care of, so that now you do not need to worry whether source teams informs you that they are doing these kind of changes, and you can manage those automatically. So when you're dealing with 5K or 10K tables, this really becomes a big pain if no schema changes at source. Again, we do this mostly for structured sources. Not for unstructured sources, maybe you are just getting plain string of lines from Kafka. We rather use static schemas, because there you can expect things might go wrong when you're actually getting data from log files. Last layer comes is about compaction and deduplication. So this is one of the costliest layer, and this is where we'll try to probably optimize it. So in case of let's say you're ingesting from MySQL source, you may have a record which is getting updated at source. So if you want to keep at Hadoop Data Lake in the same way, then you have to perform that deduplication as well in you can say your processing pipeline. And that is normally a little expensive thing to do, because you have to rewrite those files by kind of deduplicating it. And I think we had a great session on Hoodie around it, which tries to optimize this by not really rewriting the entire file, but rather doing it in an efficient way. So we'll try to explore that as well to see if we can embed that library in this deduplication layer. Once that is done, this data frame is now handed over to sync layer, wherein currently we have two syncs, which is like Hive and S3. We keep in Hive so that all the ad hoc analytics as well as those cases which run on Data Lake cluster can leverage it. But yeah, we also write it on S3 because there are multiple other clusters which kind of consume data from us in their own cluster, so they just directly consume from S3. How do we write it? It's an interesting area of its own. Let's also talk about that. So when you're writing data to HDFS via, let's say, Spark, and at the same time you have exposed tables to end users as an Hive table, there can be chances of inconsistencies if you are writing directly on the same path where people are reading without taking a lock, right? And if you take a lock, then again, if you do very frequent ingestion, that can also cause problems, because that will degrade performance. So what we have done is we have leveraged HDFS snapshot feature to kind of provide a lock-free ingestion, a lock-free table writes, and which doesn't impact readers. So how we do it? Basically, there is a base path. Let's say marketplace sales order is the base path, And within that, we have a partitions, which are like date partition directories. So we write using Spark on these directories. And at times, there may be updates in existing directories, and at times, there may be new directories getting added as well. So when we are doing it, readers are not really reading it. But once we are done writing to this base path, we take HDFS snapshot, which is a lightweight snapshot. It just kind of keeps whatever has changed since the last run. It doesn't really keep a full copy. And it's a read-only snapshot, so you cannot modify it. So what you see is on top, red line, red, you can say boxes are like base directory. And then below, you have green boxes as well as purple boxes. So these are mostly like snapshots over a period of time that we are taking as we are doing ingestion. And then we are exposing Hive tables on top of these snapshots instead of the base directory. And users are actually exposed a view so that we can change view pointer over a period of time rather than exposing those tables directly. So this helps in a couple of things. One is like you do not expose base directories directly to the user, so you're writing your base directories and which readers are not really reading to. Secondly, it also helps to maintain, you can say, versions of your data in a way that somebody wants to go back in time and see what was my data kind of looking like at that day or at that point. You can just switch to that table or view of that particular date and see what was my data at that point. And when we move this, you can say, pointer of view to the temporary tables, it's like a very lightweight operation. It doesn't really consume too much of resources. So that way, it kind of helps in writing without interfering readers. Same thing goes with S3 also. Our S3 storage structure also has something similar, so that when we are writing and there are readers to those directory structure, they do not really get impacted because of writes happening. So what we do is, again, we have a base path in S3. Then we have, you can say, versions, which we maintain over a period of time. You can also call it as epochs. So T1, T2, T3 that you see in the slide are kind of versions for every run. And in that run, whatever new data has arrived or existing partitions have changed, we write those partitions. So in case of T1, you can see 3 directories getting written for date 1, 2, and 3. For T2, a new directory for date 4 was written, but existing directory of date 2 was getting updated. And again, at T3, you can see 4 was getting updated and 5 was getting kind of added new. So all the green boxes you see are the latest partition versions for each of those partitions, and the yellow ones you can say are now stale ones. So now what we need is, once we do it, we also need a mechanism to make sure that somebody, if they want to read, they can read this latest snapshot of all the partitions. For that, we maintain the metadata in, again, Dataset service, which we call it as S3 manifest API. This S3 manifest API just maintains a mapping of partition and its latest path in S3, so that any point of time when consumers query to this query to S3, they just query from our API to get the latest partition paths, and that is consistent at that point of time. When they query again, maybe ingestion has already ran, and then they'll get a new set of paths. But they can also go back in time and say, okay, what was my state on 2 days back for this table? Then they can actually get it again, that state. But again, we maintain only limited set of versions. We do not maintain, like, we can say for years worth of versions, because that would add a lot of storage layers. So we typically maintain 15 to 20 days or a month based on use cases. Last comes Sanity, which is again a core component of this system, which makes sure that the data that is ingested is 100% correct. So just to give one example of where things may go wrong, let's say you are doing an incremental ingestion from MySQL data source. It may happen that, let's say, you have ingested till T5 point in time, the dashed line that you see, and some records get updated in source table with back timestamp, let's say something at T3 or T4. Then next ingestion run wouldn't really pick it up, because now it has already moved its pointer to the T5 time frame. So this happens mostly because of some issues at source. Maybe they have some bugs, or in some rare cases, we have also seen there are long-running transactions. So until they commit, these records are not visible to the slave machines. But we need to find out these cases and re-ingest them, and also kind of let source team inform that these are happening, and they can fix those issues at their end. So for that, we run Sanity jobs. These Sanity jobs again leverage the same connector interface that we talked about for ingestion, but they do not really fetch entire data from source, but rather what they do is just fetch the minimum information needed for Sanity. So in case of incremental ingestion, we need minimum of primary key and update timestamp column. Based on that, we do deduplication. So we kind of fetch those records and verify whether these records also exist in Hadoop Data Lake. Because you have columnar format, which is Parquet, this is relatively a lightweight operation. You do not really end up reading entire data, but just limited set of columns. In some cases, we also do simple count diff. For incremental, simple count diff may not work, because by the time you actually do a Sanity, it may have happened that some of the sources from some of the records in sources may have updated to new window, which is yet to be ingested in Hive. So that's why we have to go, for missing records, we have to go with primary key plus timestamp kind of Sanity. But then we can go for those cases wherein we do not expect records to update, we can directly go for count kind of Sanity. So we do a count diff. And in some rare cases, we have also seen duplicates coming into system, maybe because of some bugs at our end or some different reasons. So we also do a duplicate check in Sanity and publish those reports in Dataset service. Again, Dataset service, as I mentioned, is a central meta store for all kind of operations that we do. And based on that, we also identify what all partitions had issues, and we kind of regenerate a ingestion request for them, which custom scheduler picks it up in next run, and then kind of re-ingest those missing records from those partitions. So kind of it fixes the you can say Sanity issues that we had in our system. So last slide, where I'm talking about just recapping all the different factors that we have discussed about reliability. So with Spark, we are now maintaining just one code base and just writing different connectors for each source. Do not need to maintain separate code bases for each of these sources. That simplifies your monitoring, scheduling, transformation, schema evolution, and compaction, which is deduplication. You're writing less code, means there is less chance of bugs. We talked about dependency management via record time, wherein we ensure that downstream systems, when they run, they get full data because they are storing this, capturing this metadata in Dataset service, which is max record time that we have ingested data for. We talked about HDFS snapshots, which we leverage for read time consistencies. And S3 manifest API, similar to HDFS snapshot, we use S3 manifest API to kind of keep data in version way and provide the final snapshot version. S3 doesn't really have that snapshotting feature that HDFS provides, hence we have to go for a different way of providing read time consistencies. And finally, we talked about Sanity, which also adds a reliability factor, and we kind of fixes if there are any issues. So that's all from my end. In case you have any questions, you can ask.